So this problem is a great first problem to do in this friction chapter of statics because it really displays what sort of mindset you want to apply to these sort of friction, tipping, slipping types of problems. So we need to figure out how much force we can safely apply so that this crate doesn't move. So what is the maximum amount of force we can apply so that this crate does not tip over about this point and such that it does not start to slide across the ground. And they also give us the coefficient of static friction between this wooden crate and my ground. So what we need to do is we need to imagine that we're the ones pushing on this crate. And we have to imagine that we start our pushing force at about 0, but we start increasing our pushing force and we keep pushing with stronger force. As we keep increasing our pushing force, eventually the crate will start to move. The question is, which will happen? Will the crate start to rotate first? Or maybe it starts to slide first. As we're increasing that force, one of these situations will be the one that actually happens. So in this case, as I increase that force, sliding is the thing that happens. But maybe if the friction was different, or maybe if the dimensions of the crate were different, maybe in another situation, if I kept increasing that force, it would start to rotate first. So what we're going to do is we're going to write up the math for each one of these situations. And we're going to place it on this sort of force chart here so we can figure out which one will occur first as we're increasing our force. And therefore, that's the one that actually happens. So if the crate rotates, so here's our crate. Of course, we have the weight applied at the center of gravity, 250 pounds. We have our P force applied around here. Now we also have the normal force. Now remember, like we talked about in the lesson, if I'm stipulating, if I'm saying that the crate is about to rotate, that means we're about to rotate about this point right here, which means these little crate ground contact points right here, they're just about to lift off each other. So all of our normal force is basically concentrated at this one point right here, that tipping point. So here's where my normal force is being applied in this situation. And of course, friction will be acting, and of course it will be static friction. But we don't know if the maximum static friction needs to be brought out here. So you don't write this. You only write this when we're saying the crate is about to slide. And of course I have my dimensions. So remember, the crate is not moving. It's just about to rotate about this point, but it's not moving yet. It's just about to. So because of that, we still have our equilibrium statics equations that we can use. And some of the moments about some point must equal 0 as well. Well, let's go to this one first. I'm going to sum my moments about that tipping point, which is point A in the picture. Super convenient for us because it cancels out these two forces. So this actually is a really easy equation. As always, I'll assume that counterclockwise rotations are positive. And what do I got? Well, I got the P force whose moment arm is that 4.5. Its moment will be negative. And I got the moment created by the weight applied at that center of gravity, and its moment arm is this 1.5 right there. So we can solve for P, and we'll get that it's a positive 83.3. So what our math is telling us here is that it takes 83.3 pounds of force to cause this crate to rotate, to tip. So over here on my chart, I'm going to reflect that. I'm going to say that it takes 83.3 pounds to cause rotation to happen. Now we could figure out our friction force and our normal force, but I'm actually going to switch gears and I'm going to write up the math for the crate sliding. Now remember, the free body diagram that depicts the crate just about to slide is a bit different. As we push with more force up there like that, these little crate ground interfaces are going to be easing up on each other. They're not going to be lifting off, but they're going to be pressing against each other less firmly. So there's going to be less force over there on the left and more normal force on the right. So all in total, our sort of total normal force is going to be closer to this point A over here. So here's our normal force. Of course, we'll still have that frictional force of static friction. But this time, because we're saying that the crate is just about to slide, I can say that our static friction force is all maxed out. It's giving all it can with this maximum. Remember, this value is the maximum force that static friction can give right before it lets out and the object starts to slide. So in this case, we know that our coefficient is 8.4. Again, these three equations apply because this thing's just about to slide. It's not moving currently, it's just about to, as we're stipulating here. So these three equations still apply, but let's use this one. So I'm going to sum the forces in the x. We have P pushing to the right, and we have that force of maximum static friction trying to keep us still to the left. Too many unknowns here. If I figure out my normal force, I could figure out the pushing force that's needed. So I'll do my sum forces in the y. And we have the weight pushing us down and the normal force holding us up. So it's pretty easy to see that the normal force is equal to 250. So putting that in here, we'll get that P will equal 100. So what this means for us is if our pushing force is 100 pounds, then this crate will start to slide. So I got to take this back to my diagram over here. This is where I've done the math and it's now time for me to analyze the data and make a conclusion. The sliding situation requires a force of 100. So again, let's imagine that we're up there pushing. We start our force small, and we're increasing it, nothing's moving, nothing's moving, nothing's moving, and once we increase our pushing force to that 83, then the thing starts to tip. So, the answer to the question is that 83 pounds of force is the maximum force that can be applied without causing any movement. And you might hear that the crate tips first. I've heard that around a lot. And technically, it's impossible to get P to 100 because once my pushing force increases to 83, the thing has fallen over. And it's lying on the ground. So it's really impossible to get my P force up to that 100 with this free body diagram applied. So you really want to get into this habit of thinking and visualizing the problem, because this is how all of these friction, sliding, tipping problems work. Alright, hope everything made sense. If you have any questions,